This is Mr. Ellison, and this is a video walkthrough for pre-calculus assignment p5.7 in the school year 2020-2021. So let's do it. Here we go. All right. So here's problem number 1. Pole of 8-foot height is located on top of a house right on the edge of the ceiling. From a point on the ground, the angle of elevation to the top of the house is 17 degrees. The angle of the elevation to the top of the pole is 21.8 degrees. Find the height of the house. So, I think what I'm going to do, no, I can't. Better go get a Jamboard. All right, so here's a Jamboard. Sorry, that took a couple of moments here to get that, but now we got it, so here we go. So the Trig word problem there, I think that's copyable. Let's see if I can paste it on the Jamboard. Paste. I can paste it on the Jamboard. Good. That'll make things easier. All right. Stick that right up there in the corner. And now we're rocking and rolling. Okay. So here we go. Except the frighteningly thick pen I'm forced to use. Oh, wait. I can use the Jamboard pen. Excellent. That's right. Oh, let me use that. There. There we go. Okay. So first thing we want to do is draw this thing out and in a simpler form. So we're going to have, this is an 8-foot pole, and it's located on top of some sort of building, right? And we are told that the angle to the top of the pole, if you're standing some certain amount of feet away, we'll go with feet because the pole's 8 feet. The angle to the elevation to the angle of elevation to the top of the pole, that angle right there is 21.8 degrees. Okay, and then we're told the angle to the top of the house, this angle right there, that's 17. Is that what it says? 17 degrees. All right. So now we got to figure out what's what. What we're trying to do is figure out what? We are trying to figure out the height of the house. Okay, so we want to put in a variable for the height of the house. This is what we actually want to figure out right here. Okay? That's what we're trying to figure out. So we got 2 triangles. We got some angles. So the next thing to do, at least I think is the best thing to do, and I'm the teacher, so that doesn't mean you have to do it my way, but I'm just telling you. All right, so we want to just start writing in things that we know. So for instance, we know right now, we know what that angle is, right? Or at least it's easy to calculate because it's going to be 21.8 minus 17. So let's start with that. 21.8 minus 17. So that angle equals 4.8. Okay, so that's something. 4.8 degrees right there. All right, this is a right triangle right there. We know that. I'm just starting to put in things we know. So 17 degrees is that angle of elevation, and that's 90. And the 3 angles of a triangle have to add up to 180. So if I go 90 for the right triangle minus 17 for the angle over here, that angle right there, then, so what I'm solving right now, I'm solving this triangle right here. I'm going to solve for this angle. Okay? Whoops, for that angle right there. And so that's going to be 90 minus 17, because the three angles of a triangle have to add up to 180. So that's going to be 73 degrees. Now, I'm going to do a lot here, and I'm going to get more information than we need. But by just kind of going through this, we learn a lot. So a line is 180 degrees. So if that's 73 degrees, it's a supplementary, complementary, I can't remember. Anyway, that other angle has to be 180 minus 73. So this angle here has to be 107. All right. And we already know the other angle in that triangle is 4.8, which means that we can now find this angle, right? Because the three interior angles of a triangle always add up to 180. So we'll go 180 minus 107 minus 4.8. And we're going to get this angle is going to be 68.2 degrees. Yeah, we're getting a lot of stuff, aren't we? We're getting a lot of stuff. So, do we know anything else? All right, so I'm going to change colors here so we can keep going ahead. All right, so now what we're looking for is ways to find out things. Law of sines, law of cosines, Pythagorean theorem, just the kind of different sine, cosine, and tangent, different things that we might know about things. So if we have a side, we know this is 8 feet, right? We know that's 8 feet. And then we know the opposing angle from that side is 4.8 degrees. So if we know that, we are very close to figuring out x. But what we need, the triangle that has x as one of the legs, we don't know any of the legs for. So we're going to use this side here to find this length here. And then once we find that length, I shouldn't have called it x. That was bad. And I could have used undo instead of scribbling out. So we'll call this, let's call it h, because it's the hypotenuse of this triangle right there, anyways, of the right triangle. So we're going to use that 8-foot length and the 4.8 degrees to find h. So that's going to be the law of sines. And the law of sines says that we'll put the length, you can put the length or the sine of the angle on top, either one, but we're going to do the length because we're looking for a length, and it's just easier if the length ends up on top. So the law of sines says that the length of one leg of a triangle, the ratio of the length of one leg of a triangle to the sine of its opposing angle, so the sine of 4.8, that's going to equal the length of another leg of the same triangle and the sine of its opposing angle. So I got the leg is h, and the opposing, it's hard to see because it's an oblique triangle, but the angle that's opposite this h is this angle right there, 68.2. So sine of 68.2. 68, I'll make sure I put that 8 in there, and a point. All right, so now we multiply both sides by 68.2, and we get this equation, sine of 68.2 times 8 over sine of 4.8 equals h. And we're almost at h already, aren't we? 8 divided by the sine of 4.8 equals that. And we'll multiply that times the sine of 68.2. And we get 88. So h equals 88.8, we'll call it. 88.8 equals h. So we'll put that in here. 88 point, I don't know why I did that. 88.8 is the length there. And now we can use sine, let's see, well, what do we know the hypotenuse. And well, we know 73, we know both interior angles. We know the 73 right there, and we know this 17 right there, and we know the hypotenuse, and we're looking for this x right there. And so because it's a right triangle, we don't have to think in terms of law of sines and cosines anymore. We can just think of so, ka, toa, right? And that means that sine of an angle is the opposite leg over the hypotenuse. The cosine of an angle is the adjacent leg over a hypotenuse. And the tangent of an angle is the opposite leg over the adjacent leg of a triangle. And so we can use well, we can't use tangent because we don't know those legs. But we can use, let's use 17 degrees. So we got this angle. So the opposite leg is the one we're looking for, right? So that means that the sine of that angle, 17 degrees, is going to equal the opposite leg, so over the hypotenuse, 88.7, 88.8, excuse me. So then we're going to get 88. We'll multiply both sides by 88.8. 88.8 times the sine of 17 degrees equals x. And now we have our building height, just about. 88.8 times the sine of 17 degrees. We get 20. I remember this problem from before. The answer is 25 point. It's actually, if we're rounding it, it's going to be 26 feet. 26 feet. That's the height of the building. Yeah, that's a really tall single-story building with one door. And that just goes to show you, again, that they don't always do things to scale. All right, so that's one problem. And probably I'll just do like 3 problems. And then hopefully that will set you going. Let's see here. Erase. Can I erase the whole thing? Nope, doesn't look like I can. Can I do that? Nope. Oh, okay. There's probably like a clear frame right there. Bam. Bam. There we go. Okay. So let's go get another word problem. All right. We'll copy that and paste it in. Since that seems to be working pretty good. Paste. Here it comes. All right. Here we go. Linda measures the angle of elevation from a point on the ground to the top of a tree and finds it to be 35 degrees. She then walks 20 meters towards the tree and finds the angle of elevation from this new point at the top of the tree to be 45 degrees. So this is actually a super interesting little thing, because if you have something pretty simple that can measure the angle of elevation, angle of elevation is above the horizon, angle of depression is below the horizon, but you pretty easily can get a pretty accurate estimate of something as giant as the height of a mountain if you have a pretty simple inclinometer, I think it's called. It's not very expensive, and you could even kind of make one with a protractor if you wanted to. But anyway, that's enough of that. So so now we're going to draw. We've got a tree. And I'm just going to stylize our tree a little bit. I like to do a little bit of art, so I remember it's a tree. And she looks up at the tree from somewhere. And she sees that angle is 35 degrees. Then she walks. How far does she walk? She walks 20 meters. And then she looks up again and finds that angle, I'm just going to draw the ground there. She finds that angle is 45 degrees. So that's everything we have in the problem. And now what we're supposed to do is find out how tall that tree is. And it's not going to be a huge deal. But again, I'm going to put in a bunch of stuff that we know. So what do we know? Let's see, what do we know? we know if that's 45 degrees, then we're going to know this angle right there, right? Because that's going to be 180 minus 45. Okay, so that's going to be that angle is going to be 135, right? And if that angle is 135, then we can certainly figure out this angle here, because that's the third interior angle, and the three interior angles of any triangle add up to 180 degrees. So we do 180 minus 135 minus 35, and we get 10. So that angle is 10 degrees. All right. So we could figure out a lot more if we wanted to. We can assume a 90-degree angle there, which means we could assume a 45-degree angle right there. Well, not assume, that's a calculated angle, which means that this whole angle, if we care about it, is what? That's going to be 55 degrees, right? And that looks like an angle we might want, because we are almost done solving the problem. Again, we're going to use the law of sines because we have, now I'm going to switch colors again so you can see where I'm working. So we're going to start with this. Oh, that's the color I drew in. All right, so now I got to switch to this. So we've got this side right here, this 20-meter side, and the opposite angle to that 20-meter side is the 10-degree angle. And if we use that, we can then use the 135-degree angle to find the length of this side. And once we find the length of that side, we'll be far on our way, because then we'll just worry about the whole large triangle with 35 degrees and the right triangle at the tree. And it'll be a quick solve. So first things first, we're looking for a length. So we're going to put the length on top. So 20 meters over the sine of 10 degrees equals x. That's that distance, right? And then what's the opposite angle to x? It is that one right there, right? The 20 length goes to that angle, and that angle goes to that angle, right? So that's going to be x over the sine of 135. So then we'll multiply both sides by the sine of 135, and we'll get sine of 135 times 20 over the sine of 10 degrees. We should keep that degree symbol in there, because, you know, we're starting to work in radians now too, so we got to be careful. So now we'll just do this. 20 divided by the sine of 10 degrees equals that times the sine of 135 degrees equals 81. 81.4 equals x. All right? So now x equals 81.4. And that's a hypotenuse. Now we're going to work with this. I'll change color one more time. I think I have one more color. Indeed, I do. So now, last step, we're going to work with this giant triangle. We're thinking about this whole triangle right here, because that has a right angle at the bottom. And we're thinking about that whole triangle. We don't know how far away she's standing. All we know is that she went 20 meters, right? But because we know she went 20 meters and she measured this angle, that gave us this angle, and that gave us what we need. So now we are working with this side right there and this angle to figure out how high this thing is. I should make that an h, just because we already used x. All right, so we know an angle. And we could use the 10, but this is, well, no, actually, we could use 55, or we could use 35. So we're going to use 35. H is the opposite, right? So let's remember those trig functions for right triangles. So ka, toa, right? And h is the opposite, so we're going to use the sine of 35 degrees equals the opposite leg, h, over the hypotenuse, 81.4. So 81.4 times the sine of 35 degrees equals h. Here we go. 81.4 times the sine of 35 degrees equals h. Make sure it looks like I did that right. I got 46.7. 46.7 feet. That's how high the tree is. So that is something right there. And does that like sort of ring true? Yeah, it does. 35, that's a less than 45. If that's 35 and that's 80, yeah, that seems about right. That seems about right. Okay, let's see if maybe we want to do one more and then let you do the other ones. Let's see which ones. The top of a 7-meter high building, the angle of, okay, that one. How high is the mountain? We just did that, only with a tree, so we don't need to do that one again. You're standing at the base of a large building with a flag on top. The height of the building and the flag together is 323, the angle of elevation. Okay, so that's pretty much that flag, different thing, flagpole part. The river, don't worry about number 6 because that, well, actually, hang on. Okay, let's see. I'm going to do 3 because it's got an angle of inclination and depression, elevation, excuse me, and depression. So we'll go back over here, clear that, and we'll paste our new problem onto there. And hopefully we won't make this video too much longer because I know they can get long, but on the other hand, that's what needs to happen, right? So we'll start with black here. And from the top of a 7-meter high building, okay, so that's 7 meters. This one is really deceptively easy, as you're going to see. From the top of a 7-meter high building, the angle of elevation to the top of a cable tower is 65, and the angle of depression to its foot is 45. Okay, so I didn't really draw this quite right to scale, but too bad for that. So that's going to act like our tower. And we've got an angle, so when it talks about the angle of elevation and depression, okay? So the angle of elevation is going to be this one, that's 60. And the angle of depression is going to be that one, and that's 45. 60 degrees and 45 degrees. And they want to know, how high is that tower in meters? Which we can figure out. All right? So here we go. Let's do it. What do we know? We know a lot. I'll get the red pen for how much we know. Okay, so that tower we're assuming is straight up. So that's going to be a 90-degree angle. And if that's going to be a 90-degree angle and it's got a 45, that means that this angle here is also 45 degrees. And if that is straight up and down, that means this angle here is also 45 degrees, which means that this angle here is also 45 degrees. And if you have, that's why I didn't draw this well, but if you have something like this with a 45-degree angle here and here, that means it's a box, square, which means that this is also 7 meters from here to here. And if that's 7 meters, that means that this is also 7 meters, the distance straight to the tower. And if the building height is 7 meters, then this part of the tower is also going to be 7 meters, right? See how much we already know? Holy cow, we really just we know a lot more than we think we do, so we just need to start writing stuff down. What else? We know if that's 60 and that's a 90-degree angle, then that must be 30 degrees right there, right? 30 degrees right there. And so what we need to do is find this piece right there. And we have a 60-degree angle there, and we have an opposite. The opposite would be the x. That's the opposite. The adjacent is the 7 meters. And tangent works perfectly for that. So katoa. So katoa, tangent of an angle equals the opposite leg over the adjacent leg. So the tangent, in this case, of 60 degrees is going to equal the opposite leg. That's the x that we're trying to find out, right there. And the adjacent leg is this piece right here that is touching the angle, right? So that's what adjacent means, is touching the angle. So that's 7. So then we'll multiply both sides by 7, and 7 times the tangent of 60 degrees equals x equals what? That's what we have to figure out. 7 times the tangent of 60 degrees equals 12.1. 12.1. So this piece up here is 12.1. And it doesn't look like it the way I drew it, but remember 60 is actually bigger than 45. So if I was going to redraw that more accurately, I would have started with the angles. I would have gone like, that's 60 and that's 45 right there. And it would have looked something more like this. And with that's the building that person's standing on, right? And that's a 60. That's what it would have looked like, and that's a 45. So that, and then you can see everything better. Drawing to scale, roughly to scale at least helps. Okay, so now we have 7 meters for the lower part and 12.1 meters for the upper part, and 7 and 12.1 is 19.1. So that's pretty much how you do all those. And I think that that's enough for you to be going on with the rest. So the main thing, just to reinforce, draw the whole thing out, label everything, label all the givens, like what the problem gives you in terms of the data, right? The different lengths and the angles. And then just look at it and say, well, what can I immediately calculate, just like quickly, just like pluses and minuses and whatever, things like that, based on what I know that triangles, the interior angles add up to 360, supplementary angles, 180 add up to 180 degrees, complementary ones add up to 90, things like, that's that kind of stuff like that. And then once you do that, then you start using your deepening knowledge of trigonometric functions to solve these kind of problems. And I hope that helps. And I'm just going to end the video there and wish you a very lovely day. Bye.